Hello everyone and welcome to this lecture. In the last lecture we have started the discussion on regular graphs, right? So regular graphs are the graphs where every vertex has the same degree, and the degree is d, we call it d-regular graph, okay? And then we find some properties of this, especially the largest eigenvalue with the corresponding eigenvector. Then what is the largest possible size of any independent set? Basically we have given one bound on that size. Okay, today we will discuss a very interesting class of regular graphs that we call strongly regular graphs. Okay, very beautiful structures. So let me first give you an example, some examples rather, of strongly regular graphs, and then I will define what are those. Okay, so examples: strongly regular graphs. Starting I always make mistakes in writing. Strongly regular graphs. Okay, regular graphs. Okay, so let us take few examples. Very good. Let me first give you some examples. So let us first consider C4. Okay, then let me number them: 1 2 3 4. Then C5, yes, C6. Let me do it quickly. Very good. And let me take one more. So let me number 1 2 3 4 5. 1 2 3 4 5 6. Okay, and let me take one more graph that we famously call Peterson graph. Okay, so let me draw that graph for you. Hopefully I will draw it correctly. Sorry about drawing earlier and vertex I have denoted as circle, but now I am denoting at points. Okay, so very good. This is Peterson graph. Okay, Peterson graph. Okay, now let me first tell you which are strongly regular, which are non-strongly without defining them. 6 7 8 9 10. Okay, and then you analyze, I mean, what is the property where things are strongly. So this is a strongly regular, this is also strongly regular, this is not strongly regular, this is strongly regular. Now think, I mean, what is such property which is making them strongly regular and this, right? Basically, I mean, I'm now defining those. Okay, so the graphs for which every two non-adjacent vertices has fixed number of, I mean, the constant number of common neighbors for every two pair of non-adjacent. Similarly, every two adjacent pair of vertices have some constant number of neighbors. Okay, so for example, if you see here, in let's say C4, every two non-adjacent vertices have two common neighbors, and every adjacent neighbor has neighbors. Every two adjacent pair has no common neighbor. Okay, in case of C5, every adjacent pair has no common neighbor. Okay, and but every non-adjacent have one common neighbor. But this property is not followed by C6. In fact, any Cn which is greater or equal to where n is greater or equal to 6. Peterson graph is again strongly regular. If you see that any two non-adjacent vertices have one common neighbor, for example, 4 and 2 are two non-adjacent vertices, but they have a common vertex which is 3 here. But every two adjacent vertices does not have any common neighbor, right? You see. Okay, so a strongly regular graph. Okay, so a graph, a d-regular graph where every pair of adjacent vertices has a constant number of common neighbors say A, okay, so A number of common, and every pair of non-adjacent vertices has similarly a constant number of common neighbors. Okay, so say B. Okay, very good. And we will denote such a graph by, we will denote it by n is number of vertices, right? D is the degree, A is the number of common neighbors between any two non-adjacent vertices, and B is the number of common neighbors between any two non-adjacent vertices. Okay, now very good. So I hope the definition is clear. Okay, what about its eigenvalues? We will shortly see that these guys, I mean these strongly regular graphs, display very nice beautiful properties of eigenvalues. In fact, by eigenvalues we can in fact determine whether the graph is strongly regular or not, if it is given that it is regular. Okay, so let us move to find the eigenvalues. Okay, so eigenvalues of strongly regular graphs. Okay, so SRG, strongly regular graphs. Let us calculate them. Let us calculate. Suppose AG is adjacency matrix. Suppose the AG is the adjacency matrix. Is the adjacency matrix of a strongly regular graph Z. Okay, now if you see, let us observe about A square G. What will be the entries in A square? G? If you see that A square G, the ijth entry of A square G will give you what? The number of walks of length 2 between I and J, right? The walk of length 2 between I and J is telling what? The common neighbors, right? The common neighbors. The number of common neighbors, whatever the common neighbors will be, we will reach from I to that common neighbor, and then from that common neighbor we will reach to J, right? So this is a 2 length. Okay, so the number of common neighbors will tell you the number of 2 length walk between I and J, right? One thing. What will be the basically the diagonal entries of A square G? What will be the ith diagonal entry of A square G? It will tell you are going from that I, going by one edge and then coming back to the same edge, right? Okay, so basically that's how this 2 length walk will be. This is a closed walk of 2 length, right? This is nothing but degree of I, right? So A square, so let us see what A square entries are. So if I equal to J, basically then the A square G is nothing but A square G, basically II is the degree of degree of ith vertex, right, vertex, which is equal to d. Very simple, right? On the diagonal of a square g there will be d. Okay, very good. What about non-diagonals? Okay, otherwise if I is not equal to j, basically off diagonal, and I and j has an edge, the I and j has edge between them, then what will be a square, sorry, I am making again the a g, what will be this, O comma j. I am extremely sorry, I might be frustrating you with my writing. Okay, then a square g ij will be what? The number of common neighbors between I and j when I and j are adjacent. So what is that? This is equal to a. Clear, right? Very simple by definition. If again I is not equal to j and I does not have an edge between, then similarly we can say that the common neighbors between them is b. Okay, so I hope my pen is working. Very good. Yeah. So now how can you write a square g in terms of a? How can you write a square g in terms of? It's now very simple that a square g, if you see that a square g, or let me write just a square, okay, equal to, on the diagonal there will be d, right? So I can write d times identity matrix, suppose there are n vertices, then plus off diagonal entry when I is not equal to j but they have an edge between them, then those entries will be equal to a, right? So this is a times ag. Then the last term is what? The last term is when they do not have an edge. In that case it will be b, right? But how to mention this, how to represent this? Basically whenever in a there are zeros, right, in a square ij we will have b, right? So this I can represent by, this matrix I can represent by, if you see carefully, let me write this simply. So this will be, basically I will subtract, okay, so wherever there will be 1 I will make 0, where will be 0 I will make 1, but diagonal entries I have to still remove. So j minus a will do this complement thing, but I have to remove the diagonal entries, okay, and then this is b. Okay, now this is given to us from the definition of adjacency matrix or a definition of a strongly regular graph. How can we make use of this equation to find the eigenvalues of a square, of a rather, right? Remember, the largest eigenvalue we already know. The largest eigenvalue we already know. What is that? The largest eigenvalue is d. Suppose, I mean, let me do it for just strongly connected adjacency matrix of G. I assume that this is connected. Okay. For disconnected, I mean, just a union of this. So let me connected, union of connected components or connected graphs. Let us take it. Okay. Now how can, so largest eigenvalue, so by default lambda 1 equal to d, and we also know the corresponding eigenvector, one of the corresponding eigenvector corresponding to d is all 1, right? The corresponding eigenvector is all 1, right? All 1 vector. Now this all 1 vector, that means what? It is orthogonal to rest of the other eigenvectors of it, because A is symmetric, we can always choose such, right? So what will be the, how can we make use of this equation? How can we make use of this fact, right? So let us lambda be some other eigenvalue. So suppose Ax is equal to lambda x, where lambda is other than 1, other than d, other than D. Okay, so what will happen if you multiply x here, both, I mean everywhere, right? So this will be basically a square x equal to d times x plus a g x. Okay, and then this guy will be b j minus a minus identity times x. Now if you see it carefully, this will give you lambda square x, right? Very good. This is what? This is dx, nothing special here. A lambda x, very good, from there. And then interesting thing happen here, b times, if you do this, what will be j into x? Remember, j is consist of all one vectors, so rows are all one. If you take dot product with x, if you multiply this all one with x, it will give you 0, right? So this quantity is nothing but minus lambda x because of this, and this is minus x, right? So I can now write, what? Now remember, this x has to be non-zero vector because it's an eigenvector. So this implies I can cancel x from both hand side. So this will give you lambda square equal to d plus a lambda. Okay, hopefully I am doing it correctly. Then plus b minus lambda minus 1. Okay, maybe I can take lambda at this side, so this will give you, this will imply that lambda square, and then maybe what I can do is plus lambda b, I will take as b and minus here a. Okay, is it all? Then plus b minus d, yes, b minus d, yes, very good. I think, let me check it again. So lambda square, lambda I have taken, so b, yeah, minus a, then plus b minus d, perfectly fine, perfect. Now this is what? This is a quadratic equation. So surprisingly, this test there will be two eigenvalues, two other eigenvalues of strongly regular graphs. Okay, and these eigenvalues will be given by this. I mean, let me, I do not want to solve because this could be quite lengthy. So lambda plus minus, so one eigen will be plus, one eigen will be minus, right? So this you can give by just what? A minus b, right? And plus minus what will be this? A square root of some quantity. Let me write it bigger, theta, and this divided by 2, right? Where theta will be what? Where theta will be this, right? So theta is nothing but your, yeah, b minus 4 AC, right? So what will be that? Yeah, so this will be 4, yeah, d minus b. Hopefully I am doing it. So these are just calculations. Okay, so there will be two, other than d, there will be two more eigenvalues. But what about the multiplicity? Can we find the multiplicities? Indeed, yes, about the multiplicities. Okay, multiplicity. Okay, what will be? So suppose lambda plus has multiplicity m plus, okay, and lambda minus has multiplicity m minus 1. Sorry, m minus. So these are multiplicities. Okay, so how to find them? Okay, one trivial thing is what? The summation of all the eigenvalues is equal to 0, trace is equal to 0. So basically d plus m plus times lambda plus m minus times lambda minus, this is equal to 0, right? So this is what? Trace is equal to, so one equation. And another thing is what? How many eigenvalues are there? There are n eigenvalues, right? N eigenvalues. So basically nothing but 1 plus m plus m minus, this will be equal to n. And we know what lambda plus lambda, oh, so there are two equations, two unknowns, so we will solve. Okay, so very good, very good. And before moving to next, next very beautiful fact about this, let me give you one DIY. Okay, simple case. Find the eigenvalues and their multiplicities of ND11. Very good. There is one more thing that maybe I have missed it. So whenever we are considering d-regular graphs, okay, strongly regular graphs, ignore basically other than, so the other than, ignore complete graph, other than, sorry, this I am mentioning at last, but other than kn, complete graph, and empty graph. Basically there is no edges. Okay, so empty graph and very good. Okay, very good. Okay, now let us move to next interesting topic. Okay, so let me write the result, the next interesting result. Yeah, okay, so let G be a connected regular graph with three distinct eigenvalues, then it is a strongly regular graph. It is a kind of if and only if statement, right? Earlier just we have proven that if graph is strongly regular, we were able to get three distinct eigenvalues, right? I mean, this you have to prove why this will be distinct is not very difficult to see. And now when there are three distinct eigenvalues, the graph is strongly regular. And remember, we are talking about regular graphs. Okay, so proof, okay. So I mean, we have assumed that the graph is not complete graph and it is not empty graph, null graph. Okay, so we are talking about other regular graphs. Okay, very good. So now suppose these eigenvalues, remember it is, if it is a d-regular graph, right? Suppose I have not said regular, so suppose this is d-regular graph. Suppose G is a d-regular graph, so then what? The largest eigenvalue, so lambda 1 is equal to d, and it is connected also. I think I need to have some water. What about the other eigenvalue? So let me call it lambda 2, lambda 3, and they are distinct, right? So they are distinct. Okay, so now other eigenvalues are lambda 2 and lambda 3. Now remember, I mean, let me write one polynomial and you will recognize what I am going to do next. So A minus di, this matrix, so this is a matrix, then A minus lambda 2i and A minus lambda 3i. Okay, this matrix will be 0. I will give you one hint why it is 0. The proof actually I have done in when I was proving that the diameter can be is strictly lesser than the number of distinct eigenvalues of graph. In that way, in that proof, I have made use of such polynomial, and then I have proved that any vector x will be in the null space of it, okay, of this polynomial. Okay, basically if you multiply with x, any vector x, it will be 0. That means the rank of this matrix is 0. That means this matrix is 0. The whole matrix is 0. Okay, Okay, so and why it is so? Because A is adjacent, it's a symmetric matrix. We can always find an independent or an orthogonal eigenvector, and you can represent any x with linear combination of this. Now let us just focus on, for some time being, A minus di. If you see that A minus di, so d is eigenvalue corresponding to the largest eigenvalue, corresponding to the so d is largest eigenvalue. What will be its corresponding eigenvector? The eigenvector corresponding to eigenvector for d will be nothing but some alpha times some constant time is some constant time all 1, right? It's a multiple of all 1, right? All 1 vector. Okay, so c times 1. What does this imply? So basically, if you see the null space of it, null space of A, basically null space of A minus di, okay, it just follows from that eigenvalue eigenvector definition, Ax is equal to lambda. So right now here A1 equal to D1, right? So null space of this is nothing but consisting of all the vectors of types C into 1. Okay, right? So that means what? So if you make this 0, so this, I mean this is 0, that means what? So this implies that all the columns of this guy, this implies that, sorry, all the columns of A minus lambda, and this is also, I mean, since this is connected graph, so multiplicity of D is exactly 1. Multiplicity of D is actually, that's why there is exactly 1. I mean, basically the eigen kind of the null space has rank, or the dimension of null space is 1. Okay, so A minus lambda 2, A minus lambda 3, all the columns of this guy is actually is multiple of 1. Okay, so this is all 1 means all 1 vector. Okay, now so again let me for all 1. Okay, so I mean, but this matrix is symmetric. This matrix is symmetric. That means every column will be of same type. That this implies as the matrix is matrix is symmetric. Okay, this implies that this is nothing but A minus lambda 2i, A minus lambda 3i is nothing but some alpha times some alpha, maybe I can use alpha, right? Some for some constant alpha equal to j for some alpha, right? Now what does this imply? What it implies? Okay, this implies that you can indeed write A square h, if you open this, A square can be written as some combination of some linear combination of A comma I comma j, and hence like this, right? We have actually by the definition of strongly regular graph, okay, this was happening here. There's a linear combination of I, j, and j. Okay, so this in fact I'm sorry, I have lost somewhere some text. Okay, yeah, this is A square can be written as some linear combination of this. Hence by the definition, by the definition G is strongly regular graph. G is a strongly regular graph. Very beautiful theorem. Okay, so basically now if you combine both this result and the previous result, it says that if G is regular connected graph, then it has 3 eigenvalues if and only if it is strongly regular. Okay, with this I am stopping this lecture, and in the next lecture we will prove a very beautiful theorem, something called friendship theorem, using strongly regular graphs. Okay, so thank you very much. Yeah.